You can get started. As I mentioned yesterday, I know how stressful this week is, and I also know how difficult the current assignment is. So as I mentioned, please reach out to me, and I will be especially understanding with regards to if you'd like to shift your focus to the recursion assignment, because that pulls directly from the ape, or not from this ape, but from historical past apes. And those are good practice problems for thinking about recursion. I will need both of those assignments in by next Wednesday. In the absolute worst case, the reason is that we will be having an exam a week from Friday. So I want to make sure that you get those in, and I at least give the grader a chance to try to get them back to you ahead of the exam. And depending on how many people push off that submission, that will be more or less feasible. So I would like there to be, if it's possible to get them in sooner, that would be great, because then I can get more people all of that feedback ahead of the exam. But if your priorities are studying for the eight, that's okay. That will just be the downside to that, as you might not get quite as much feedback on assignments ahead of the next exam. Questions about where we are, what we're doing, where we're headed in this class, or anything else with regards to the eighth or this class's place, or anything else before we dive in?
So I take it Monday, you were mostly going over recursion and that sort of idea.
Yes, I've done quite a few of the recursion examples now, but yeah, if you were curious, there is a lecture video posted on YouTube that goes over exactly what we went over. I recommend looking at that. Yeah, it's lots of recursion examples the last couple of classes. And we have, including this one, 4 more to go. Lots of examples over the next couple of days. So some people said they finished off an iterative Fibonacci. Did anyone finish a recursive Fibonacci? Hey, few people, awesome. So we're going to finish these off first thing, and then we'll dive into the next one. So what do we need to do after these base cases? So we say if n is less than or equal to 1, return n as your cases. If we pass in 0, we get 0 as the 0th Fibonacci number. If we pass in 1, we get 1 as the first Fibonacci number. But now we need to start coming up with some logic of how we're going to calculate the next Fibonacci number, and the next Fibonacci number, and the next Fibonacci number, keeping track of that. So I'm going to say that we have one more variable here. It's not strictly necessary, but it makes life just a little bit easier. It needs some value here, but it's a dummy value. And we'll go into a loop. We want to continue to calculate the next Fibonacci number and the next Fibonacci number until we get to n. But this isn't going to start where most loops start, at least for my solution. There are plenty of solutions to this. But if we've already returned, if we've calculated the 0th or the first Fibonacci number, if n is 0 or 1, then we can start out by saying, well, what is Fibonacci number 2? So let's figure out how we can do the logic for this. So we're going to start out a counting variable here at 2 rather than 0 or 1, the usual, saying this is going to calculate the second Fibonacci number. We want to continue this process while this is less than or equal to n, since we want to figure out the nth Fibonacci number. And if this is going to be the first pass through this loop would calculate the second Fibonacci number, then we want to continue this process while I is less than or equal to n, and we'll bump it up each pass through the loop. What do we want to do inside of this loop to actually have the second Fibonacci number stored somewhere, but also updating where the last couple, because we know we're adding the Fibonacci number at whatever the current value of I is, -1 and -2. So we need to update those values as well. I've stored those initial values in first and second. Yeah,
What do you want to do? Something like current equals first plus second, and then first equals second, and second equals current?
that is exactly what we want to do. So if we say current equals first plus second, this calculates the next Fibonacci number. This is Fibonacci number 2. First plus second is basically, first is going to look back 2 ago, second is going to look back 1 ago. So adding them together gets the new Fibonacci number. Then we need to update the value of first and second for then in preparation for the next pass through the loop. In the next pass through the loop, what's going to be 1 ago and 2 ago? So 2 ago, which we call first, is what is currently 1 ago. And what is currently 1 ago is going to be what we just calculated. Then we would loop back around and bump up I. We're ready to calculate the third Fibonacci number. The third Fibonacci number would be calculated right here and stored in current. In preparation for calculating the fourth Fibonacci number, we would need to store in second, the second Fibonacci number, which is currently stored in first. Sorry, it's currently stored in second. We will store that in first, and then the 1 ago. Question?
2 plus 1. That's still right.
That would work initially. But as the Fibonacci sequence evolves, it will be more than 1 apart. Once it becomes, it was 3, then 5, then 8, then 13, then 21. So it starts out being 1. So if we did, let's kind of show you what that would look like. So all we have to do now is return current at the end of the loop. Once the loop terminates, it's the last thing we wanted to do. And let's take a look at the effect that that would have. So let's write a main. We'll print out, again, an iterative version of this, and then we will call Fibonacci recursive and pass it, I don't know, what's something that we can easily verify. Let's go for second Fibonacci number is 1, and then 2, and then 3, and then 5, 8. Let's do 6. That should give us 8, which it does. 7 should give us 13, which it does. So you said second equals second plus 1 here as a potential. So we do something like second plus plus. We run that, we would get something that is just a little bit off. And I think it would get slightly more off the larger value we got here. So 13's next is 21. So if we calculate 8 here, we get 13. It looks like it's bumping it up a little bit slower than the growth rate that we would expect. Good idea though. Any questions about how this works or why this works? Draw it out in more detail. How do we feel? Maybe sets of thumbs to let me know. Totally understand it. Understand it. Kind of sort of, you draw it out a little bit. Lost. Don't know what this code is doing. Okay. Yeah, let's run through a quick example. I think that would be worth doing. So we said that Fibonacci iterative of 8 is 13. Let's actually go through and figure out what it's doing. So let's write out the Fibonacci sequence and make sure that, so we have 0, 1, 1, 2, 3, 5, 8, 13. So that's what we're trying to get to, is that 13. This is the Fibonacci sequence, and we'll see why this sequence works as we go through the code. So we have some variables along the side here. We have a first, we have a second, and we have a current. So we start first and second out at 0 and 1, and these become the first two special cases. We're not calculating these. We return them if we see that as a query. Other than that, we store them as the initial value, and the goal of this loop is to calculate the next Fibonacci number. So current is set to a dummy value that I'm not going to replicate at the moment. But we come into the loop and say, is I, which when we passed in I was 8, is 2 less than or equal to 8? Yes, we'll come into the loop. Current equals first plus second. So this is calculating the I minus 2th plus I minus 1th Fibonacci numbers to calculate this value, the next value here that goes in current. Then we need to update in preparation for calculating the next one. So to do this, we're going to set what is currently in first to be, with a new value of first is the old value of second. So we're kind of moving first from here to there. And then when we say second equals current, since we just calculated current as the next element of this sequence, then we're taking second and moving it up 1 as well by saying second equals current. So the equivalent logic of having done this is instead of the box being drawn around these first two numbers, the box is now drawn around these two numbers as storing first and second. And as we loop around, the goal will now be to calculate the next Fibonacci number. So we say current equals, since we just wrote first to be 1, first plus second, 1 plus 1 is 2. So we overwrite current with 2. So that is, if this were the end, this would be what we would return. But in preparation for the next pass, we need to update. We're going to say the value of first gets the current value of second. That doesn't change anything, but second gets current. So we're going to move that box, which again does the exact same thing of bumping this box up by 1. So in the next pass, we're looking at this 1 and 2 in preparation for calculating the next one. Coming into the loop, current equals first plus second. So we're going to write 3 here, and in preparation for the next pass, we just bump everything up 1 spot. So first becomes the current second, which is 2. And second becomes the current, which is 3. So now if we were done, we'd return the 3. But since we're not, we loop back around. Draw the box over the next one. So calculate current, first plus second, 5. Then we overwrite, second goes to first, that becomes 3. And current goes to second, which becomes 5. You can see how this is kind of flowing from current backwards to second to first, and then out of the scope of the problem as this box is sliding across the Fibonacci sequence. Calculating the next value, sliding the window, the old one falls off. Calculating the new value, sliding the window, old one falls off. So that process is happening over and over until we reach the target value, the nth value, and then we return that. Does that help? Okay, so now we want to do the exact same logic, but recursively. So instead of using a loop, yeah, questions?
Sorry, I formed on the iterative.
Yeah,
I did that all a little bit differently. I was gonna make sure it still works.
Yeah.
Like the code, I was gonna see like. Anyway, I set current equal to just first, and then first equal to first plus second, or like first plus gets second,
yeah.
and then second gets current. So it's a little bit different.
It might just be the names that are different. The names of your variables representing the different.
All of that's the exact same.
Yeah. That should still work, I think. Yeah, there are many ways to do this. I just, whenever I write something like this, I tend to think of how is it going to be easiest to explain or easiest to draw out and map directly to code. So there is no better or worse answer as far as I'm concerned right now. If you came up with a solution, that is great. There are an infinite number of correct ones. So yeah, if you did not get exactly this, no worries. So thinking about this recursively. What changes?
That would be like a base case.
Yeah, we need to start thinking about a base case and a recursive case. So. What's a base case? What's a value of a Fibonacci sequence that we're going to know what it is? First of all, how many base cases are there going to be? Because we've now seen a couple of examples. The first one where there was one base case, but when we looked at the last problem we went over, the power of two, there were two base cases. So two base cases again here?
You know, like 0 and 1 and then all.
Yeah, yeah.
So probably base case of all of those.
Yeah, if you write out a problem iteratively and you think, all right, my first instinct is to set these values. There are two variables that receive these values and they represent the first two elements of the Fibonacci sequence. This is because you need those first two as a base to begin the calculation. So when you write this recursively, you will also need two base cases, one that refers to each one of these cases. That will help you to be able to identify that. Luckily, this if can be completely borrowed for that. This will become your if statement for those base cases. Right? If we want to figure out the Fibonacci value of 0 or 1, it is 0 or 1. It is the actual index into the Fibonacci sequence. So let's actually go write that. We don't need this line anymore, just fit as much on the screen as I can. So let's write Fibonacci recursive. We said we can borrow this for our base cases. I buy that. I think this is the first thing that starts. If n is less than or equal to 1, we will return n. What do we do after this? What's the base case look like? Yeah,
So n less than equals 1, return n is our for two base cases,
Yeah.
right?
yep,
And then we just, I have a line, right?
Yeah.
Return, Fibonacci recursive n minus 1
mhm.
plus Fibonacci sequence n minus 2. And recursive.
Are we completely done with that one line? Is there any other implementation to do? What does this do? Just describe, if you can, a little bit of what happens. Well, I'm just gonna write a tester and see if this magically works. What do we think? What are we gonna get? Is it gonna work? Just slightly off. No, it's not. It's the same. Look at that, it works. Will it work for other values? We tested 5 before. Is it gonna work for 5? Get the same value. Is it gonna work for 20? Look at that, it does. Is it going to work for 30? It does. Is it going to work for 40? Why am I still testing this? Whoa, the iterative finished immediately and the recursive took a second. Iterative finishes, in fact, it's an integer out of bounds, but recursive is still working. It's still working. Yeah,
I just have a question about recursive. So you said Fibonacci recursive n minus 1 plus N-2, could you minus 2?
Yeah, I'll go into why that is, but this is still running. In fact, if I make this slightly more than 40, it's like 42 and 42. That was just a little bit more than what we had before. In fact, now we're still in bounds. That took a little bit. What's the limit here? There we go. That's taking a little bit longer. That took a few seconds. Does anyone get a hint as to why the recursive version is taking longer while we explain exactly what's happening here? Because I think the issue and exactly what's happening here are interrelated. Yeah, yeah, we're storing them as we go.
Yeah, so then first I can't find them, it's like, it was movie. Has to like search through everything and then.
No, it's not doing a ton of searching. It's actually doing, yeah,
Well, is iterative like takes up more memory, but then recursive sits on
it actually is less, it is probably significantly less memory to do the iterative version. So Fibonacci is one case where I'm introducing this as a very nice, short recursive version, but in this particular implementation of Fibonacci, this is a garbage implementation for efficiency. And in fact, this is a problem in Java that you should do iteratively and not recursively. Why is that efficiency so bad?
Start and then go all the way down the list.
It is not even a V. Like that, I like that, I really like that visualization of a recursive process where you're going, recursive call down to a base case and then back up. That is a great idea, except that the visualization for this recursion is not a V. It's something much more complicated. Yeah,
Would it have to go down and up for each time it goes down?
kind of.
Yeah.
So let's look at what happens for Fibonacci of 8. I'm just gonna write this as 8, and this means the calculation for the 8th Fibonacci number. If we're doing this iteratively, we just go right up the chain using 0 and 1 to calculate 2, 1 and 2 to calculate 3, 2 and 3 to calculate 4, 3 and 4 to calculate 5, etc. But what's happening recursively? So let's take a look at, to do this, you have to calculate Fibonacci recursive of n-1 and n-2. So this means that we're taking Fibonacci of 7 and adding it to Fibonacci of 6. But to even get to the point where we can start calculating this Fibonacci recursive 6, we need to evaluate Fibonacci 7. This is going to break down into 7 minus 1 and 7 minus 2, which is 6 and 5. To even get to this 5, we need to evaluate this 6, which is going to break down into Fibonacci of 5 and Fibonacci of 4. This is going to break down into 4 and 3. This is going to break down into 3 and 2. This is going to break down into 2 and 1. This is going to break down into 1 and 0, both of which are base cases, and we can solve them. We come back, this is a base case, we can solve that. But now this has to break down into 1 and 0. Coming back, we get back to this 3. Wouldn't it be nice if we stored the answer somehow from this whole tree? Because now we have to repeat all of the work of this subtree as we calculate 3, which is 2 and 1. This breaks down into 1 and 0. This 4 breaks down into 3 and 2. This 3 breaks down into 2 and 1. You can see how this is a lot of work and a lot of repeated work. And this is before even considering this 6 is this entire subtree. This 5 is this entire subtree. So you can, again, we're doing a lot of repeated work. Completely, totally unnecessary repeated work. If we could intelligently store things as we are working.
Is that the recursive case?
Yeah, this is what's happening recursively. This is how many calls we are doing.
So then the iterative is 7.
Yeah, because it's just not doing as much work. And when you get up to something as bad as recursive 44, you can imagine that what's actually going on underneath the hood is a truly massive tree. To make a computer like this sit and think for a few seconds, that's billions of calculations. That means there are probably billions of nodes within this tree that it's calculating. So rather than just, if we do this iteratively, go right up the chain to 44 and have an answer. In a linear amount of time, how much time is this recursive version taking? How many nodes are there with proportion to this 8 in this tree? If we could calculate that out, we have, let's make a table. We're gonna go down 8, 7, 6, 5. We'll just start there. There's 1, 8. So we're calculating Fibonacci of 8 once. There's 1, 7. There are 2 6s. If we broke this 6 down, there'd be a 5 and a 4. So there'd be 3 5s. How many 4s would there be? Would there be an extra 4 for each one of these 5s? This would be a 4 and a 3, and a 4 and a 3. So how many 4s we have? 1, 2, 3, 4, 5. Holy shit, it's the Fibonacci sequence. We just remade the Fibonacci sequence and how many nodes in a tree we needed to calculate the Fibonacci sequence. You feel like this is Inception, and recursion kind of feels like Inception as well. This is just kind of the fun we start having in computer science. You break it down and start analyzing it, and things happen. But it's interesting to see the sequence appear in the representation of the sequence. But it ends up being a ton of work. Significantly more work than a linear iterative version. Is there any way we can fix this? Yeah. What could we do to prevent doing this significant amount of work recursively? Yeah.
I don't know, but it would have to still. Cause I was looking at it, but then it seemed like you'd still just have to do exactly what you were doing before.
Yeah.
And
There are 2 algorithmic techniques for this. One of which you will learn in algorithms next quarter, and I'll briefly describe it here, so when you see it, you can tie it back to this idea. And the other I kind of hinted at earlier. It is not a sort. So the first one is what we call tail recursion. And that's less relevant to this problem. Because tail recursion is something that you can do rather than when you come back up the recursive chain. You're repeating or doing something along the way before you can output an answer. So here's where you start, here's the base case. Here you're coming back up the recursive chain to where you have an answer. I would argue that anytime you can represent a problem like this, you can also represent it like this, where you store a partial solution along the way, and in fact, are communicating that solution as a hidden parameter. And this is another reason that we method overload. I will eventually have an example of this, a better example of this for you, where I can show you exactly what this would look like. Unfortunately, Java doesn't really support tail recursion, but this also allows you to bypass the Stack Overflow exception. Because when you're done with this particular stack frame, you're not going to come back to it like you are in this case. You're passing the answer along, and since you never need this, intelligently, we can just get rid of it. You don't need to store it to come back to it, even though that happens. So if the recursion is the very last thing that happens in a method call, it is called tail recursive. This is not tail recursive because when we come back from this and come back from this, there's something we have to do. We have to do some math on the result of that recursion. However, it is tail recursive if the very last thing, return some recursive call. If that's all it is, a single recursive call with no math, then it is tail recursive.
Could you just get rid of the plus sign and limit 2, or would that? You have the Fibonacci recursion and -1 parentheses plus parentheses and -2.
Yeah, you have to have some way of embedding that in the call or embedding that in some information that's passed along to. The idea would be that when we get down here, we have our total answer. We don't have to do the rest of the work of this tree. We just calculate and pass along the information as we go. We can do that. That is possible. Any idea how? It ends up actually looking very much like the iterative version. You calculate the next Fibonacci number, and by the time you reach down to 0, the cumulative value that you have accumulated looks kind of like the iterative version. You start with the Fibonacci value of 0 or 1, and then each time you recurse, you calculate the next Fibonacci number underneath the hood until you get down to that value where you can return it. And recursively, now you've implemented the iterative version of that. So that would be how you do this tail recursion. The other version is called dynamic programming, and it involves an algorithmic technique you'll see in CSCD 320 that involves intelligently storing things as you go. So the amount of work in this tree could be significantly reduced if the first time we calculated something, it was a lookup. So if we want to calculate Fibonacci of 8, we see that it requires Fibonacci 7, Fibonacci 6. So let's just store in a table, some other table somewhere, the values of all of the Fibonacci's that we have seen so far. So that instead of having a calculation at this point, that's an entire subtree, this is a lookup in this table. So every time we calculate something for the first time, we can use an element from this table to calculate it because we're also not calculating it from scratch. So this unknown, skip it for now, break it down into this. This unknown, skip it, break it down. Eventually you get down to the base cases. This gives you Fibonacci of 2. And now forever, whenever you see Fibonacci of 2, it's a lookup. And you can use Fibonacci of 2 and everything you know so far to calculate Fibonacci of 3 in constant time. And you can use that and everything you know in your table as a lookup to calculate Fibonacci of 4. Likewise, you can do that bubbling all the way up the tree to the top. And you take something that is exponential in size and you pare it down to something that is linear in size. Everything all the way up here is a single calculation or a single lookup. And the tree is now sized, instead of exponential, is actually sized linear. So you can take a problem that takes a very long time and you can break it down into something that, if you intelligently store the information as you calculate partial results, you can break a problem down into a bunch of lookups and then significantly reduce the amount of time that your program takes to run. So that's coming in 320. Hopefully, at least a little bit of that sticks around for that. My goal is that's a pretty tough unit in that course. And dynamic programming comes up over and over and over in upper division computer science courses, in interviews. This becomes something that really queries, do you know algorithmic techniques? So companies love to use dynamic programming examples. That was a big aside, but kind of an important one. Questions on anything from Fibonacci before we move on? For now, this is okay. It is very bad in terms of its complexity. But what is better than that requires stuff that's a little bit outside of the scope of the course, but I just want to throw it at you so that when you see it again, there's something tickling in the back of your mind. I've seen this before. What was that? Questions? How do we feel about Fibonacci recursive now that we've kind of seen it drawn out as a tree? Thumbs? Feel okay about it? We'll get more practice. I think that's okay for now from what I see. So the next one I'm going to do is one that's actually directly off the homework, except I'm going to do it for array lists rather than the implemented linked lists that we've done. So my goal is that this helps you with that homework. But we're going to have a list and we want to reverse that list. How are we going to think about reversing a list recursively? So that's an interesting idea. Thinking about it iteratively. Again, I'm not going to actually write this iteratively. But if you were trying to reverse a list, how would you do it? You have an array list of, let's call it 10 elements. And you want the element in the last position to now come first. You want what's in the first position to now come last. You want what's in the second position to come second to last, and what's in the second to last position to come second. How would you do it?
You would have to have some sort of temp thing to store your first position, whatever it is. You just take whatever your first position is, store it in the temp, take your second position, move it to your end position, whatever your end position is, move it to the first, and then take your temp, and then move it to the second.
Okay, so yeah, doing a swap of those values. Yeah, you want to start with the first, something that represents the first element, something that represents the last element. You're going to swap those and then move them inwards. Swap, move inwards, swap, move inwards until they cross. Once they cross, you're done. That would be a nice iterative version. You can imagine writing that as a loop. How do we think about this recursively? What's the base case? What's the recursive case? This one's a little bit different, just thinking about it. So take a couple minutes, talk to your neighbors and see if you can identify what's the recursive breakdown of this problem. Question. Around this, the angle brackets,
No, you're focusing on.
around this whole thing, that's the parameter, because this is the name of the function. So we have public static, the return type is a list, an array list. The function's name is list reverse, and it takes one parameter, an array list.
So that's it's not the base case, we call the function. That could be something like. Sorry, plus one. Minus one.
Oh, yeah, she handed that to go over it.
Any brilliant ideas out there? What have we thought of? Yeah,
I was just thinking that you could just make a new list, and once the new list is the size of the old list, you know you've gone through the entire list.
yes,
Backwards, the list size.
but that would also be iterative.
How would it?
That would be iterative in nature. Or at least we could structure it iteratively. I can argue that we can do this without making a new list. Just with the existing structure of this list. What's the base case? What is what would it look like for a list reverse to be already done? Or something where it's so simple that it can be done easily. There's 0 or 1 elements in the list, yeah. So if you want to reverse a list of size 1, it's already done. If you want to reverse a list of size 0, it's already done. So now the question is, how can we take this list and turn it into a list of that associated size? The key idea is that each one of these recursive calls is its own scope, meaning it has its own local variables. It has its own local everything. So what could you store from the existing list before you modify the existing list so that you can work your way toward a base case with a single element in it or no elements in it? Good. Which element would you want to store? It's a great idea.
Left in color stuff and right in the fall and slowly and. Like increase your government that index and ways to increase the first of the whole.
That is an iterative way of thinking. It would absolutely solve the problem. But with that idea, I would want to write a loop for it.
When you want to store the element before you're gonna remove it, so that you're getting down to the base.
Which element? That's exactly right, but there is a correct element to store. The first element, that's exactly right. Thinking about this from the perspective of a list of size, let's start with something really small, 3. We have 1, 2, 3 stored in an array list. I'm drawing it as an array because that's what it is underneath the hood. So 1, 2, 3, great. What happens if we store off from this perspective just the number 1? in something. What can we do to this list now that we've stored the one? We're actually just going to straight up remove the one from the list. It's gone. We're going to pass this on to the next iteration of the recursion as the list that needs to be reversed. We take the first element, we store it. What's left is this list of one element, and we pass that along the recursive chain. Coming in here, we see we're in a base case. This list is already reversed. We're going to backtrack to this place where we say, with this list that already exists, we are going to append this thing that we stored to the end of it. Add at the end. That's something a list knows how to do. So when we pass this back up the recursive chain here, what we're passing back is 3, 2. When we come back here, we're going to take what we stored in this recursive call, and we're going to append it to the end of the list. So we get 3, 2, 1, which we return from the original call, and that is the reversed list. Question?
So do you need a variable to store like each number that you're setting up, or do you need a variable for one, you need a variable for two?
Yes, but it's the same variable.
Okay.
Because it's a recursive version, each different scope has a different version of that value. So we'll see it as we write it out. I'm actually going to write it with this drawing still on the board. I think that will help people see why we're writing it the way that we are. So we passed in this list. How do we do it? What do we need to do? We need to figure out if we're in a base case. What identifies the base case? You should have some kind of if statement. Yeah,
The list size is less than or equal to 1.
if the list size is less than or equal to 1. Then we just return the list. Because this expects to return a list. So we're basically saying it's already reversed. No further work needs to be done. If we get past this, and remember, when we return something, we don't need to worry about writing an else for something like this. We're not going to reach this line of this method unless this if was false. So we don't need an else.
Why do you have the information less than the list?
Because if the list is of size 0, it's already reversed. If the list is of size 1, it's already reversed.
How's it already reversed?
I have a list of size 0. I have a list with nothing in it. If I were to call the reverse procedure on this, just the concept of reversing that list of 0 elements, what would the correct answer be for that list reversed? A list of 0 elements. Yeah, so we're going to define a reversal of a 0 element list as itself. And the same thing for a list of size 1. Let's quickly finish this off. We're going to store in some value, I'm actually going to call this something that we're used to, the tail. This is the tail of the new list that we're going to be appending at the end, but we're going to say this is the current head. So we're going to say list.get 0. Then we are going to remove it. So we're going through the exact, whatever's drawn on the board, the work that I did there, we're going through each one of those steps. We're getting the element at the beginning, we're removing it. Then we're going to set the list, because this function returns a list, to be, we're going to make the recursive call. That's just going to pass it down the recursive chain. From this particular perspective, what happens after this is magic. Once this is returned, what happens? We know that The remainder of the list, aside from this one element that we removed, has been reversed. So what do we need to do? We just need to add it to the end and return the list. That's the whole function. We run this and we see that it is in fact reversed. I can justify this just a little bit more at the start of next class and or in office hours, but we are unfortunately out of time. I will come back to this at the start of next class though, and talk about, we can run through exactly what's happening line by line here in the code. It'll make it, tie it to this visual diagram. But I'll see you for that tomorrow. Office hours for the next couple hours if you have questions.